session. You are 75% of the way through this workshop. We still have a lot of wonderful visual goodness for you. All right. There we go. All right, ladies and gentlemen, our first speaker in this session is Alyssa Goodman. Yay.
Hi. I'm Alyssa. Hi. I was asked to talk to you today about augmented reality and glue, but I think I have to talk to you about glue first before I can talk to you about augmented reality and glue. And I think maybe the most important thing, according to Jackie, is yes, there are stickers. Yes, there are sticky notes. Yes, there are augmented reality target cubes, but you only get one of these if you pay attention to this whole talk and find out that you can go to the AAS booth and become a user tester in the augmented reality experiments that are going on at this meeting. Okay, now you don't have to remember anything else. Okay, so what is glue? I will tell you in a moment. And then I will give you a very, very tiny sneak preview of a press conference that a wonderful recent graduate of the University of Virginia, Theo O'Neill, will be giving on Wednesday using work that relies on glue. And then I will show you some videos and live demo afterwards, if you'd like, of how this augmented reality new feature of glue works. And because I didn't know who was going to be in the room, some of you might have seen I was trying to do a survey on Slack. I've brought you our most advertising-y look, very generic introduction to glue instead of our very astronomy-specific introduction to glue. So I'm going to start with that. And I'm just going to tell you, let me move the annoying Zoom thing. Hang on, you don't need to see me. That all the slides are live and all of the links that are in the slides are live as well. And so I'll just stick those on my website when we're done. So you don't really have to write stuff down while I'm going here. So here we go with the fastest introduction to glue and the most generic introduction I can give you. And then I will explain what it is in terms of what I can do in astronomy. But importantly, glue was named by Chris Beaumont, who was its original developer, and it's not an acronym. It has functionality, okay, that glues together data sets, glues graphs and different kinds of data displays together. And as you just heard recently, also glues tools together. So in terms of data, it literally can mean anything, okay? So it can mean a table, binary arrays, spreadsheets. In terms of formats, in terms of images and maps, it can be any number of dimensions. It can be fits. I didn't even put here HDF5, JPEG, GIS formats, anything you want. And like I said, high dimensional data is glue's forte. And so what happens is there's a user interface where you can either graphically or algorithmically define links between the different data sets, saying what are their shared attributes. So a very simple example would be, let's say right ascension and declination are called right ascension and declination in an image. And then you have another file, which is a table with 3,000 columns, but two of them are called RA and Dec. You can tell the program that the ones that says RA is the same that says right ascension, okay? You can also make all kinds of much more sophisticated linkages between the data sets, but a lot of people actually use only the identity links. Okay, but that means that you don't ever have to build some gigantic data file with some specially defined format for your number of dimensions. And then in terms of what kinds of graphs, basically if you're familiar, raise your hand if you use Python in any way, shape, or form. Fantastic. Okay, so if I say that you can have any matplotlib graph you want, you can have any matplotlib graph you want. And then you can also, by the way, this is what wearing a mask does to my voice because it sucks all the water out. Anyway, you can also have all kinds of plugins, which I'll get to in a moment. But there are a lot of Python graphical packages that go beyond matplotlib these days. And then there's maps and images with all kinds of control of the images, like what you've been seeing in some of the previous talks. And then you can also work with 3 dimensions, volumetric rendering, layered plots, and you can make all kinds of specialized plots as well. So the really key feature of glue is this gluing together the different kinds of plots. So if you make a selection, as Jackie was showing you very quickly in her demo about using glue inside of OpenSpace, if you say, oh, that's my interesting data, and then that same data will highlight across all of the views, and that lets you play with the data in real time. And yes, the data sets you can use are quite big, not infinitely big, but quite big, the real-time functionality works. And then if you have software that you like already or plot types that you like and they're not in Glue, you can add them by a plugin architecture. You can also use web services such as Worldwide Telescope, which is a very popular plugin to Glue, and you can do whatever you want in a command line. So you can customize Glue however you like. And so remember again that this word glue has three meanings, that it glues together data, graphs, and tools. And then because you're going to ask about this, yes, it's not just a GUI tool. You can start again where you left off by saving a Glue session, which you can also share with collaborators. You can export graphics, some of which are publication quality on their own. You can use Glue in Jupyter environments. There's a whole effort to make something called Glupyter that I'll mention later. And you can export to Plotly to make interactive figures for your colleagues and for journals, which I'll show you again in a moment. And last but not least, you can export to augmented reality. So if you don't know what Glue is, go to glueviz.org and you can go, as Jackie mentioned, download it. All right, so great. So what can you do? This is the sneak preview of the press conference I told you about for Wednesday. That is the magnetic field of the local bubble around the sun, visualized in Glue. And Theo O'Neill, who will give the press conference, will show you. Oh, don't take pictures and put them on Twitter, please. Glue, Open Space, and Worldwide Telescope all working together. And this is from a colloquium I gave now last year, showing some recent results from our own groups that used Glue. And some of you may have heard of some of these. I'll highlight one of them in a moment. But this is a three-dimensional view of a shell created by supernovae. This one on the left here, this is the so-called Perseus-Taurus supershell, and that's the one that we exported to augmented reality. On the upper right is the Radcliffe wave. These are things that I don't have time to explain how, but Glue was actually part of the discovery of these things, and you can scan the QR code in the middle if you want to know more. And then there's also the local bubble itself and the visualization of that using 3D dust mapping and the motions of the stars that showed that all the gas forming the stars was on the surface of the bubble. But just to give you an idea, this again, Jackie showed you a few minutes ago, the interface is not something we're like super proud of, but you know, it's better than nothing. And the Glupyter interface is the ones that we use in other contexts actually look much nicer because those are for people who won't put up with a confusing looking interface. But it turns out people learn to use Glue pretty quickly and they don't complain too much about the interface. But just in terms of just taking this screenshot here, looking at someone exploring the Radcliffe wave, what they've done is to load in many different data sets. This whole thing on the upper left is a long list of data sets that have all been glued together, as I showed in the simple video or demo. And then they're looking at particular regions of interest. So they're highlighting things that will show up even in Worldwide Telescope. If you highlight them within the desktop Glue environment, those selected points will go to Worldwide Telescope. And then, as I mentioned, Worldwide Telescope is one of the plugins, which is done through a web service. And I won't say more about that for now. I'll just say that I said a minute ago, it's pretty easy to use. And just to show you a very goofy video that I showed at a recent conference for science writers that they liked, so I'll show it to you too. This is our press release of last year, which actually wound up in the New York Times, showing that all star formation near the sun is on the surface of the local bubble. But this video that you'll see in the background is my collaborator, Catherine Zucker, who was the first author of that paper, and Joao Alves, our close collaborator in the whole work. The three of us were on Zoom in February of 2021. And you'll see this very, very goofy video of the three of us going, oh my goodness, okay? And so all we had done was drag the model for the local bubble, that's the sort of wispy bubbly thing you see, into a visualization of the 3D dust map of interstellar matter near the sun. And it just miraculously turned out that all of the star forming regions were on the surface of the bubble. So that's an unusual moment, in that you can actually see the discovery happening live. So this is my cat. His name is Leonardo. Are you paying attention? Because there's going to be a quiz. What's my cat's name? Excellent. Very good. Not DiCaprio. Okay. Da Vinci. He has a last name. Okay. And so Leonardo is helping demonstrate this augmented reality here. And so what we did was, again, a different shell, which was actually in one of those videos a moment ago, but that's okay. This little small shell here now, this Perseus-Taurus supershell, we output using this one button output where you can export to Plotly from an interactive graph inside of Glue. we put that in a paper. I have the paper right here. But then if you scan the QR codes that are in the paper, you have two choices. You can make the data float above a flat surface, or you can see it on one of these augmented reality target cubes. And the purpose of this cube is it's a lot easier to manipulate data, at least in my opinion. I shouldn't color our user survey. I didn't say this, but I find it easier to manipulate 3D data in my hand than to get up and walk around. But okay, so this is the fireworks are supposed to get your attention. There's a handout on the table here that will show you that you go to the AAS booth during the meeting, and there should be people there who will happily give you one of these if you will cooperate in the user testing. And I'm only going to tell you now that the user testing does not use lots of fancy astronomy data, because that's not how you do user testing if you're a visualization researcher. So it's going to seem very rudimentary, but please cooperate, and then you'll get one of these and you can make your own visualizations. Okay, so finally, what is coming next? Glue in the browser for real. So right now there's an effort which is very substantially funded, because Glue was originally supported as part of the James Webb Space Telescope visualization effort. And so something called AAS241 came out of that effort, and it's a suite of tools that uses Glue inside of Jupyter environments and inside of web pages to give you quick views of JWST data. And then there are several other uses of Glue, some of which actually don't even have anything to do with astronomy, but that inspired us to try to create a full version of Glue inside of a Jupyter lab environment. So we're collaborating directly with the Jupyter organization, and we have a grant from the NSF and from the Moore Foundation to try to bring you Glupiter. And I have a website for that you can, that's this one, and you can go see video. And then on the other side, sorry, I should go back here, just explain here what in my head, Jackie already explained this, but I should say it out loud, which is that there's this a trio here of Glue, Worldwide Telescope, and Open Space that are cooperating very nicely. And my own personal interest in this is something called MilkyWay3D.org. We're working again with our colleagues at the American Museum of Natural History to use these three programs, Worldwide Telescope, Glue, and Open Space together, to be able to just bring in every bit of data that anybody has about the structure in 3 dimensions of the local Milky Way. And we're going to make all of that public. And we're going to show more of that this week on the NASA Hyperwall. And then this is a sneak preview that David hasn't even seen. I emailed it to him. There he is. And so this is building on David Weigel's tool that he just showed you. And what it does is, here, I'll actually show you. It just lets you contextualize the JWST and Hubble images in a way very similar to what he was showing you, but it's a very, very custom purpose tool that works on a phone where you can slide back and forth between Hubble and JWST. And David and I share a dislike of people who show these images side by side and where they don't let you zoom in and out for the context. So if I can use somebody else's computer and get back to Keynote, I can finish here. Okay, whoops, sorry, that was the last slide, I believe, just reminding us about MilkyWay3D.org. And that is the end. And come ask me and I'll tell you more about this. Thank you.
So we have one question.
Uh-huh.
Slide. Can you repeat the question?
Says, what tools do you recommend for 3D rendering of AMR data? The talk mentioned Maya. What other tool do you recommend? Blender, ParaView? How do they compare? I believe that meant Frank's talk. I didn't mention Maya. But we do render 3D data, but you don't want to render huge amounts of 3D data in Glue interactively. It would be too slow. So we actually have a YT plugin to Glue, which we're trying to get to work a little bit faster. But if somebody has a really fast 3D visualization solution, please let me know. But otherwise, you do have to do what Frank was talking about and downsample the data a lot and sort of pre-render something that's manageable. And when I say big, the kind of data files we can handle, I mean, only a Glue session that I would make, you know, is embarrassingly, it can be up to like 30 gigabytes or something like that. Okay, so it can be quite big, but not 30 terabytes. Okay, so just to give you some idea. Okay. Is that it?
Other questions in the room?
Seriously? Come on. Thank you, Carter. What's your question? Yes. Oh, Carter's asking an astronomy question, which I'm happy to answer. He's asking, he thought that the local bubble was derived from the Gaia dust maps. The model of the local bubble that you see there without the vectors was in fact derived from the Gaia dust maps. But local bubble was originally discovered in X-rays and radio and all kinds of other things that kind of gave very indirect evidence that the density of the interstellar medium near the sun was much lower than farther away. And that was back to the 1970s. And but there was no information in terms of distance. In other words, you had to infer things about the distance of particular points using distance to clusters and stars and things like this. So the big deal, and this was done by Vincent Pelgrims, actually, this particular 3D map. And then what Catherine did, the discovery that was in New York Times, that was to say that all of the star formation near the sun is on the surface of the local bubble. And therefore, this theory of supernova-driven star formation probably holds a lot of water.
Thank you. While Ryan's coming up, I just wanted to note that one of you had asked about the temperature in the room. I did put in a request for them to look into that, but there's a help desk channel in the Slack. That's the only way I've reached the AAS. So we're following up the best we can.
Okay, Ryan Wyatt is back with with actually some cool planetarium stuff. Got this is in the wrong place. I'm gonna have to escape out of this. Hold on. Let's put this up in the upper right hand corner for now. You can figure out where you want it. All right. Oh, bloody hell, it did it. It did it again, didn't it? I got it back. I got it back. There you go. That's better.
Good. Thank you once again for the introduction and tech support. I guess I was completely incognizant of where I was in the camera field of view for the first time I talked, but now that I've learned that many of you either work in a planetarium or want to work in a planetarium, it kind of causes a bit of a pivot for what I was planning to say, but hopefully to kind of deepen a little bit of a background on planetariums generally, but on some thoughts if you are presenting data in a planetarium or collaborating with a planetarium and creating content, some things to keep in mind. And then because Jackie and I didn't coordinate, I'm going to plug ideas again at the very end. But this is visualization in domes is kind of the way I've framed this as opposed to sort of focused on planetariums. But of course, planetariums are have always been visualization environments. They just typically visualized only one data set, star locations. And this is the original Morrison Planetarium star projector that was built in San Francisco. We opened in 1952, which was when the only place you could buy a significant large planetarium projector was in East Germany. So we decided to build our own. This was using cutting edge technology of the day to calculate positions for the individual stars that were then, this was just the printout for show. And then those were used as locations that were essentially embedded on the star plates that projected the sky. So this was data viz, cutting edge data viz of its time. Now we have racks of computers that do that job, and the dome is actually filled. We have a 23-meter dome, uses 6 video projectors, sort of very similar to Hayden Planetarium in New York, except ours is tilted about 30 degrees. So it's a little bit more like if you went to a domed IMAX theater, it's a little bit more like that setup. And typically there are people in the audience, but not for this shot. So what's important to note is that you're really creating this huge image, as and Frank described sort of how you're with any of these sort of cinematic visualizations, you are really throwing a lot at people because you have narration, music, visuals, and it's even more so a challenge in the planetarium because you're filling people's peripheral vision. You're really, you're asking people to do a lot. So when we represent that 75-foot diameter dome, we have this sort of fisheye image that represents the entire dome. So if you can imagine, the front is of that image is in front of you, and if you're in the center of the theater, about 30 degrees down, the top of the image is behind you, and the left and right are sort of filling your field of view. So often when I'm going to show sequences from our shows, but I'm going to show you this little subset, a little HD crop of what's actually filling the entire field of view. And Robert mentioned earlier, this idea of cognitive load, that presents a lot of cognitive load. When you're trying to process this image, you're looking around, you're hearing someone yammering at you about science, and you're getting this beautiful musical soundtrack. There's a lot to think about. So when we design imagery for planetariums, we try to make sure that when we're creating visualizations, we're trying to simplify and make as direct correlation between the message that we're describing with words and the visuals that we're presenting in the dome. So I'm gonna just show a quick non-astronomical example. And this is an example from our show about earthquakes. And we wanted to, and if you look at a lot of like USGS renderings of earthquake, like surface shaking, we'll have lots of crazy color coding and all that. The important thing is the surface of Earth shakes. And so we color coded that red. And then the yellow color coding is for slip along, in this case, the San Andreas Fault. And we're using a computational simulation of the 1906 earthquake, which sort of launched earthquake science. So by keeping the visual representation as simple as possible, it makes it feasible for people when they're kind of processing all of this information that's sort of flying at them with 30 or 60 frames a second to be able to follow the story and understand what we're talking about. I'm going to do a quick little, Robert did much better sort of case studies, but I'll just do a case study for a visualization that we worked on with the National Center for Supercomputing Applications. This is data, two sets of data really that one is on the left is a giant molecular cloud with by Kritzik, simulation by Kritzik, and we wanted to show the sort of slow evolution of that, but we wanted to zoom in on a planet forming disk, but with a simulation by Aaron Boley. And initially we started out with this sort of beautiful but visualization, but it doesn't, the colors don't really convey specific meaning. So we ended up kind of pulling back and going a little more boring with this and try to create a essentially what I call sort of this photoreal in air quotes depiction of flying into a galaxy. This is a model that was developed by the National Center for Supercomputing Applications that basically is used based on imagery of another galaxy for our Milky Way. We fly into the Kritzik data, and here we do offer this sort of hint of sort of reddish glow. Part of this was inspired by and Robert referenced this as well, like if the artwork that you see that represents sort of planet forming disk uses a certain sort of color representation, we just sort of leveraged that for this in another sequence that I'll show you. And we actually used one of Robert's artistic representations of a planet forming disk as our inspiration for the coloring and the representation that we used for the computational model. So this was a way of sort of using things that were relatively familiar to people to get across the story that we wanted to tell about planet formation in the Milky Way. The next example, and hoping this will autoplay, but it won't. So this is a sequence that is actually from a different show, and and kind of bring together some of the comments that okay, how many times do I have to click the? Oh,
Did you have an external file?
I had an external file, which I just played you. That's okay. Let's just so
The external file did not get connected to my laptop. Sorry.
So so basically it shows a planet forming disk. I do have this still image, which will which I think I can kind of get to one of the punchlines for, which connects a little bit to Jackie's talk. And that is we talked about the dynamical evolution of the solar system during the migration of the outer planets, scattering material out of the disk. And what's great about the simulation is that when visualized in 3 dimensions, you can see that the particles really start out in the plane of the solar system. And by the end of the simulation, although it's not specifically mentioned in the narration, and although it's not the main point of the story, which is really about this image, the scattering of the stuff out of the solar system, you can actually see that the dynamics of the outer part of the solar system have relaxed, and you have a much higher distribution of angles around for the smaller particles in the outer solar system. So instead of a very flat disk, you have a much puffier disk of material around the solar system. And Mike Brown and Constantine Patigan, who worked on us on the data with this, commented that in our visualization, they saw things that they had not seen in their data before, which I think goes to Jackie's point, not with real-time software, but with a much more involved process that along the lines of what Frank described, that you can really produce a result that is great storytelling, while also being able to leverage new insight into the data. So for my brief wrap up, which is basically redundant from a lot of the great planetarium content that you've already heard, this is my sort of filler image to just represent real-time software. Everything I've described before has been a finely produced cinematic visualization along the lines, again, of what Frank described. But we use real-time software every day in the dome. In fact, OpenSpace has become our go-to platform for all of the real-time content that we show in Morrison Planetarium. And this offers the opportunity, first of all, if you're an astronomer who wants to come and give a talk in our dome, we collaborate with you to integrate your data into the talk so you're not confined to doing a slide presentation like this, but rather you can use immersive visualization to describe aspects of your work. But then also this, to Jackie's point, offers the opportunity to use this immersive environment as a collaboration space and as a way of contextualizing data that is not possible using a more traditional toolkit. So I wanted to kind of end with an invitation to think about your local planetarium, or maybe if you work in one, thinking about how to sort of connect some of these dots, but to look at ways to leverage this really amazing resource. And astronomy is very lucky. Not every science has sort of a branch office in every city in the country, but planetariums are everywhere. The vast majority now are digital, and it's feasible, if not challenging it with some of the platforms, to get OpenSpace or other visualization tools running. And it's a worthwhile opportunity. And I think most planetariums might be a little limited in terms of bandwidth, but with power users out there, like folks at AMNH or David or our team, we're all happy to help kind of elevate the work that happens in these various domes. So please think about planetariums as an environment for sharing and potentially doing your research. For some reason, I have 2 versions of the ideas. So I guess I wanted to double down on that. But thanks very much for your time, and thanks for coming to today's workshop.
Question? Yeah, let's see. Okay, questions?
For the talk in the planetarium, what kind of software do you use to make like PowerPoint or something else?
Repeat.
Oh, sure. So the question was what software we use for delivering talks in the planetarium. So we have a lecture series in which we invite speakers to come and give a talk. We typically ask them for their slide deck in their preferred format. And then we'll often iterate with them as we look at the content of the talk and maybe say, well, if you want to convey this concept, like Frank mentioned, the flatness of the galaxy, well, hey, well, let's do that in the dome using our software. So it becomes a conversation. The presenter is typically just presenting their PowerPoint and then or slide deck, and then we fade down the slide deck, fade up the full dome planetarium software, and just go back and forth to use both for their individual strengths. If that helps answer your question.
Yeah.
For the visualization aspect. So we primarily use OpenSpace, but also another software program called UniView, which was sort of a predecessor to OpenSpace in a commercial package. I think David has the aforementioned Evans and Sutherland system in his dome, but also it's that system itself is amenable to integrating new data. So you do rely on not just the expertise of your local planetarium to do that, but really the community, because we all know each other and we're happy to help each other get data into the various platforms. But there are a handful, there are about 6 or 7 different sort of software platforms that are used. Thanks, Ryan.
All right, thank you.
So just an update from the AAS, they are working, I understand the room temperature is being adjusted just in time for the end of our workshop. And we have one presentation, Robert, and then the show and tell interactive session. So
Yes.
please adjust as you've seen fit.
Okay.
All right. Hi there again. I promise, Gordon, I
Hold
will
on.
keep. Whoops.
I have to stop my share
All right.
and hold on a second before you start your share.
Oh, let me stop my share.
Stop your share. I need to pin your video. Great. Now you can start your share and go. Ladies and
There.
gentlemen, one more time. Robert.
One more time. I promise, Gordon, I will keep this short. I just wanted to introduce very, very briefly 2 other assets, visualization assets that may be helpful. I can't get into them in great detail, but just a show of hands from people in the room, even though I can't see any of them, but how many of you have had to go to the web and tried to search up really good, high quality public astronomical images of an illustration or a particular object? I'm going to assume a lot of you raised your hands.
You got most of the room raising a hand.
So AstroPix is a project that is supported by NASA's Universe of Learning, and its goal is to make this possible and easy and let you get to the good stuff fast. It is a collaboration that has existed now actually for over 20 years or almost 20 years, involving many of the people who've spoken today. And it is basically a chance to gather together the public image archives of some of the biggest observatories in the world in one place where you can search. There's an iPoster on this tomorrow, and Ryan and Lars have nicely volunteered to hang out there to help people answer questions in the 5:30 period. But one just very quick introduction to AstroPix, astropix.org. It's a place where we now have over 9,000 images from NASA's flagship observatories, from NOIR Lab, from ESO and the ESA archives. It's a place where you can go and basically look for an object like the Eagle Nebula. We will do a coordinate lookup like any archive and do a search and get to all of the public imagery that has been put out by these observatories at their finest public ready status. We have powerful ways of filtering to get to exactly the telescopes you want or which band of the spectrum you're interested in representing, from which publisher it may have come from. It's super easy to go and just focus on, say, the infrared imagery or the optical imagery. If you click on one of these images, you can explore and you get an interface that will give you downloads in all the available sizes. It will direct you back to the original image source if you want to look it up. It has metadata presented in these visual widgets that help you understand how far away it is, and exciting to me, how color is mapped to the spectrum to really help you interpret this in a quick, easy visual way. Many of the images come with full world coordinate system information, which lets you be one click away from contextualizing exactly where that image is using Worldwide Telescope in a pop-up window. I hope you will find this to be as useful as a resource as we want it to be. And like I said, if you want to know more, go to the poster tomorrow and bookmark astropix.org. Now, the other one I want to talk about is a project I'm not really connected to, but it is another one of the NASA Science Activation supported projects like OpenSpace, and it's NASA's EYES. It's Jason Craig out of JPL is the lead developer on it, but he could not be with us today. But I wanted to just let you know this exists and point you at some of the primary features of this. NASA EYES is a series of web-based, real-time interactive exploratory tools that are focused on both the solar system, Earth, asteroids and on exoplanets. And these real-time tools let you go in and explore data sets that are constantly kept up to date. If you go to Eyes on Exoplanets, you have a 3D database of all of the known exoplanets that are constantly updated through NASA's Exoplanet Archive as new discoveries are made, that really give you a really quick, amazing chance to contextualize every known discovered exoplanet and how they fall relative to the sun. Gives you the opportunity to click and zoom in to investigate particular systems. It will give the exoplanet with respect to the habitable zone. You can actually zoom in and get sort of artistic representations, hypothetical visualizations of the exoplanets. You have the ability to explore on the planet, the system, or the star level for these. So if you're looking for opportunities for education purposes, or even just grabbing quick graphics, I need a quick picture of a particular exoplanet system for a talk, Eyes is a wonderful way to do that. Another of the Eyes applications I'll mention is Eyes on the solar system. Now, this has got a real-time interface that shows you like any good orrery, all the planets in the all the planets in the solar system, the moons. It also has an exciting feature now. You can actually use a simple rate switch to accelerate, to speed up or slow down the solar system. It also has the opportunity to follow these guided tours that will explore asteroids and comet missions or take you to Enceladus. Built into Eyes, they have many of the NASA projects their geometry for the spacecraft are there. So for instance, a favorite of mine, the Spitzer Space Telescope, for instance, if you were curious where Spitzer is right now, you can do a quick search and oops, there we go. Oh, sorry, I clicked it. Sorry, like I said, I'm not on this software. I don't do this. But for instance, you can actually get a real-time view of how big is Spitzer compared to Hubble. There, in case you were ever curious. It's got James Webb Space Telescope. It will let you go in and actually explore where these telescopes were relative to the Earth over time and their mission histories. So I really suggest you check out eyes.nasa.gov. And if any of you, if this sparks some interest, but you want to know more, drop me a note in Slack and I can connect you with Jason Craig at JPL and you can follow up and ask him more questions. One really cool feature of NASA's Eyes is these are all also easily embedded into other web pages. So if you're looking to spice up a web page with like access to an interactive solar system or a 3D view of a particular observatory, you can just drop in a few lines of code onto a web page and you'll get this as an embedded interactive on your website. So that's all I wanted to say on those, and I'll give way for the rest of the conversation.
All right, thank you, Robert. Okay, so now we have our freeform session here at the end, where if you took our initial pre-survey, we asked if there was any questions about visualization or problems about visualization that people wanted to pose. Now, somebody came out to me earlier, I don't remember who, and said, hey, I have a visualization question. So we're going to start with that one because you came up with something. All right, so I guess I should stay up here. I'm so used to being able to wander the room. No, I should stay up here because they won't be able to hear it online unless I'm talking to the computer. All right. So would you please come up and give us the question you'd like to pose to people or a topic for discussion on this, okay? Introduce yourself. Come on up. Everyone say hi to Trisha.
Hi.
Give her a big hand for volunteering. Get
Yeah.
up here.
Yeah, so I'm Trisha Ashley. My question is actually very specific, so I did not know I was going to go first. So I have the FITS file that it's an image, and I just want to change the projection of the image, but I'm actually having a very hard time doing this. So I was wondering what tools would be good, because I've tried Python tools, reproject, and CartoPy, and both of those are failing to keep the world coordinate system or keep the image?
I actually have an answer for that.
Oh.
Yeah, so there's a software package that was developed at IPAC many years ago for the virtual observatory called Montage. It is a series of command line tools that are specifically designed for reprojecting FITS data from any projection into any projection in a flux conserving manner, in fact, so that you can actually maintain its research quality as well. Let's see, I'll find the URL and slap it in, but it's basically, it's Unix code that you can install, and it'll take a little time to kind of work up the right syntax and scripts, but it has like basically all the flexible tools that you would need to be able to do these reprojections. And so, you can just basically create a simple FITS header that is the projection you need it to be in, and then there are just through a few commands, you can then get it to get reprojected to where you need it to be.
That would be perfect. Thank you.
Okay.
Problem solved.
Yeah.
So just
All
to-
right, question one is a success. Let's keep it rolling.
So let me just ask this more general to the room. How often is this reprojections type of stuff generalized? Who here has other things that need to be done about that? But
I've used Montage. It's great. I think Montage works a bit better than
okay, so he's saying that Montage works better than HealPix. I'm just repeating a little bit because I got to talk to the computer so that people online can hear.
Yeah, I think Montage is a better job surveying lots of different things. My experience with the but it's nice. I work with the big
Okay. So Montage works better to preserve flux than something like HealPix. And Montage especially good for these all sky large scale images.
I mean, it works great for me. I mean, I tend to find that conflict protection software was bad for all sciences.
Okay.
As you look at the horizon, things get a little weird with like the pixel sizes.
Okay.
Angular size. So yeah,
Okay, it's saying that the Montage works well with these large images. Sometimes you get distortions near the horizon when you use large images. Okay. Anybody else want to talk about this subject? And has special information come on? This is the time to show just how much you know about all these topics. All right. Well, we had a couple of people, we had one person who gave us things. All right, so other questions that people have for our gathered experts. You know, this is your chance to ask somebody who's going to answer your questions. All right, in the black there. You want to come up and ask your question so that the online audience can hear it too? And then we'll see what we're going to get. Give her a hand, give her a hand. Introduce yourself as well.
Hi, my name is Erica. I would like to know what kind of degree and certifications you have to be a professional in astronomy visualization, because it feels like it's very different from astronomy research. So I would like to know how I could become an astronomy communicator like that.
So I think the answer is you have to learn the secret handshake. All right, so how did we become visualizers is sort of one of the questions that I'm hearing in that, right? All right, so I did my PhD in computer simulations, cosmological simulations, and I was steered into visualization when I got to Princeton, and a group approached us to do that IMAX film, Cosmic Voyage. And they took my PhD simulations and we worked them. And I found that when on the process of working on that film, that I had an adaptation towards doing that sort of stuff and explaining astronomy. And then Neil Tyson was in the office next to me at Princeton, and he hired me to go up to Hayden and help him build the new Hayden Planetarium. Okay, so I call myself an accidental astrophysicist because I was not in my I was on the research track. Okay, you know, I was at Princeton doing a postdoc. Okay, I did another postdoc at Columbia. Okay, that's research level stuff. And then I got sort of pulled into doing outreach. Robert told you a bit of his. Part
Yeah,
of-
let me just add to that
Go ahead.
comment as well, because when I was doing my research astronomy and when I was doing working at IPAC, when I was always doing the art. The AstroViz was something I was just doing for fun. I was doing my own sci-fi space illustrations, and when friends had press releases or activities, I just said, "Hey, let me help you with that." And I actually ended up getting art into NASA press releases just because I was volunteering my time because it was something I enjoyed doing. And that put me in a position where people then started to do it. And my suggestion is, if do the things that you would do just because you love it as a hobby, because that's how you develop your skill sets. But then those things that you've developed, those become your portfolio when an opportunity may arise.
Yeah. Kachan, would you come up here and tell us your pathway in all this? All right. He hasn't been a speaker here, but he's a really good visualizer out at Denver. And so just give us your history.
All right,
You can take off your mask.
okay, maybe 2-minute quick introduction. My name is Katrina Yu. I got my PhD at the University of Colorado, Boulder, doing star formation. But I was actually hired by the Denver Museum of Nature and Science to help develop their planetarium more than 20 years ago. So when digital planetariums were still relatively a young technology. And even though I didn't have, my experience programming was IDL, but I ended up writing scientific visualization code for placing objects in the universe for our at home, homegrown planetarium software, working with a real software programmer. So again, I think I share a lot of the attributes of other speakers in having had interest in this. I did a lot of drawing. And so through various connections, I made certain people know about my interests, and so in some ways I kind of lucked into it. But again, part of it was following my passions and interests, and I can see how things that I did in grad school that didn't seem to really have any pertinence or connection to what I would do could have in a career in research astrophysics ended up helping in the direction that I did end up taking. So again, follow your passions. Thanks.
Thank you.
I don't know if the timing will work out for you, but I get this question a lot, not just for visualization. I want to get into outreach. I want to get into education, science communication. How do I get started? One of the things we're hoping to build at Caltech IPAC is a Center for Science Communication that will bring together folks like this who are experts, let's say, in visualization, with scientists who want to grow in that field, whether to make a full up leap to become a professional or to become part-time in that. And that we would imagine you would come and spend a mini sabbatical at Caltech, spend a month, spend 2 months, work with our team, work with other experts and so on. So that's probably a year or two away, but it's the reason I wanted to mention it, would that type of resource be available, be of interest to you? If I was to say, here's a place you could come here, work with us for a couple months, get started, learn some of these basic tools, would that be useful?
Yes.
Yeah, okay, so watch this space. Hopefully this time next year, I'll tell you I have funding and the center is about to launch, so.
And also, most of you took the pre-survey. We're going to ask you to take a post-survey in just a second, but for those who want to get involved in our community of practice, this is a project under NASA's Universe of Learning. We have the AstroViz project that creates the cool visualizations, but this is the community of practice project where we are trying to develop a way of talking. I mean, amongst those of us who do it for a living, but also to bring in the folks who are interested about it. So this is the QR code for if you are interested in giving us your info, or you guys, we already have your info because you signed up for the workshop. We have your email addresses, but for you and for others that want to get involved, we have that. Are there other visualizers who'd like to give their story before we move on to the next one? Carter, you want to say anything about, because you came in from an art background. Come on. I knew he wouldn't resist. He wouldn't shy away from getting up here.
Thanks, Frank. I think, you know, I was coming from an art background. My mom used to take me to the planetarium for planetarium school, starting from age 10, drive me in from New Jersey to the Hayden Planetarium. My father was an artist, sculptor, painter, commercial artist, photographer. To me, the dioramas at the museum were and are very special. They show you a context of we've gone out and shot some animals and stuck them in context. We don't so much do that anymore. But Dennis Davidson was an artist at the planetarium. He and I actually both competed for the same job in the late 80s. He got it, I didn't, and I was jealous. But I met Dennis and we became friends. And Frank and I came on the same project together called the Digital Galaxy Project. When I was interviewed, we sat down with Neil Tyson and a little interview. I still have sketches of that day of the storyboards. And my first criticism was, why do you call it the Galaxy Project? Because you got the whole universe. And Neil said, whoa, 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 Carter. First, we have a lot of work to do with the galaxies. I said,
go like this. Whoa.
well,
Hit you on the slaps.
right. So I said, well, that's astronomy 100 years ago. What are you going to do about the rest of the universe? And so the continuity of that, and how we show that, I think is really important. I think perhaps what you've seen across a lot of these presentations today is how we show the context. Because when you gain your PhD, you've gone down some tiny little needle facet of your subject, and you're the world's expert now. And then you come out the other side of your PhD and you broaden out and you spend the rest of your life contextualizing that to a broader and broader field. I think it's important, we were talking about planetarium software, there's high-end production. So I direct the shows at the Hayden Planetarium. That's a team of about a dozen people, very talented digital artists and visualizers, putting that all together. Something like open space or other interactive tools. We heard UniView mentioned, and these are projects that I oversaw when they were developed. But those are to give you agency, and that you as a user, whether you're seeing somebody else do that in a planetarium, that's one thing. But you can spin something around, look at it this side, that side, see the relationships, whether that's in AR or VR or whatever that is. It's just getting to know that broader neighborhood better. You get to know your neighborhood by walking around or driving around. And so I think that's the important part. I think we got into it from a diversity of fields, but if you have the interest in the visual, I think you will end up in this field.
Okay.
Thanks.
Thank you. All right, you had something? You want to come up here?
That was the follow-up question that anybody else, any other background has sound, or everybody just
Right.
want to do science and what.
All right, so just for the folks online, the point being that do people only come from astronomy backgrounds to become visualizers? No. Most of my team at Space Telescope comes from design and art backgrounds. Okay, I'm the only astronomer on our 7-person team. Okay, 2 others have master's degrees in astronomy, but not PhDs. So I rely on people so let's take fonts. I don't do fonts. Okay, I know what I'm not good at. I know about the great things. I'm really good at the science and the choreography, and I have a dance background, so 3D motion and everything always is old hat to me. But if we're going to choose colors, I'm not a Robert Hurt. I'm not going to choose color. I'm not going to take a color palette. Somebody else has got to do that. So we need people from those backgrounds as well. And so at our team, we have that variation of people who can use different tools. We have image processing specialists. We also have 3D specialists. We have compositing specialists. Okay, people who specialize in each of those pieces of the pipeline. In Hollywood, you get one piece of that pipeline, or maybe you get a tiny piece of that one piece of the pipeline, okay? We have to be more jack of all trades and other things. David,
Can I say one thing?
he wants to say something. Bring up David.
Fantastic. All right. So I think really quick thing to highlight too is that we've heard from a lot of people who are at very prestigious and big places with potentially lots of money. And I don't want that to be seen as a sort of roadblock to getting started in Viz, because it doesn't need to be. And there's so many free tools that we've outlined today. And while it's amazing if you have a team who can help you out and specialize in all these sorts of things, like that's the dream, right? But if you're just you can still get going in this and be great at it as well. And immerse yourself with these, again, different variety of tools and start learning a lot of them, figure out what you like, figure out what you're good at. And that puts you in a position to still make some great visualizations, even if it is just you. And then also, it's not just you because we're this entire room. And so use everyone else as a resource as well. I think the Viz community is pretty tight knit, and this is your open invitation to be a part of it.
And I have to totally emphasize what you're doing. Part of the reasons we started doing these workshops is to bring more people in, to develop a community of practice. To help us develop that community of practice, to help us improve these workshops, bit.ly AstroViz23, or use that QR code. Give us feedback on this workshop. What did you like? What didn't you like? What would you like we would have gotten to? One of the questions that we got earlier was, hey, are we going to do any in-depth learning of one tool where, you know, I follow along on my laptop? And so that's a type of workshop that people do a lot. We chose not to do it to highlight because there's so many tools. But is there one particular tool everybody would like to learn that much more about? You tell us on this. I want to thank all of our speakers today. This has been an intense 4 hours of, you got a lot of content in these 4 hours. And you got a lot of good visuals. And unfortunately, Robert and I probably could have done 6 to 8 hours of this because there's just so much cool stuff out there. We'll continue to do this again. Thank you, all of you. And thank you all for coming. And we'll see you next time. Thank you. Robert, did you have anything you wanted to add?
No, I just, other than you don't know how much I wish I could be there to meet and continue the conversation with everyone. So hopefully we will get a chance to continue this virtually. We are looking to host more virtual meetings coming up this year to make it easier for people to jump in and join on like a 1 or 2 topic basis. So we will contact you when these things come up. And like I said, as I typed into Slack, make sure to share that link with your peers who weren't here, who maybe who couldn't get to the workshop, because the more the merrier on this.
All right. Thank you. Hey, how you doing? What's your name? Oh, Melissa, that's right.